Hi, I hope everyone can hear me fine. I know I stand between you and your coffee break, so I'll try to make this as interactive and quick as I can. Now, before I begin, just a quick show of hands. How many of you have used ChatGPT to ask a health-related question? I see quite a few hands up, and for those of you who have not thrown your hands up, there are good reasons to do and not do it, and hopefully we'll see some of those today. So it's not news that LLMs have widely made their ways into our lives, and we're using them increasingly for asking a range of different questions, right? But healthcare is such a critical domain. We really ought to know what are the strengths and limitations of these sort of technologies before they're introduced en masse. So the work that we did was called MEDIC. It was aimed at addressing and understanding what are the strengths and limitations of a range of different LLMs that are available today. It addresses a particular... Okay, I'm struggling to get the slide to go forward.
The big green button.
The big green button, yeah, doesn't seem to be working. Looks like the pointer needs some coffee as well. Okay, there we go. So just in the last couple of years alone, since the announcement of ChatGPT, we've seen a tremendous amount of activity in the area. So we've seen the big tech companies like Google launch their medical language models, and we've seen others come out from NYU, some of the local organizations like M42 as well. And a lot of these models demonstrate very impressive performances on some limited benchmarks. One that's often cited in the media is called a USMLE exam. It's a United States medical licensing exam. And a couple of months after ChatGPT was announced, a study came out that reported that ChatGPT can apparently achieve what would be considered a passing score in the USMLE exam, which led the American Medical Association to write this article. ChatGPT passed the USMLE, what does it mean for medical education? More specifically, would you trust a doctor who only passed the exam but did not actually go through the residency program? My answer is no, but I'd be curious to hear your answer as well. And this is where, again, some of the limitations of the ways in which we are looking at these LLM performances for clinical applications today come forward. In this recent JAMA article by many of the experts in this area, they noted that the existing evaluations don't assess many important dimensions such as fairness, bias, toxicity, among others, which are very important for healthcare. That's an example of a USMLE question, by the way, for those of you not seen it before. And I bet in real life your clinician does not have 4 choices to pick from, right? So it just goes on to demonstrate the sort of limitations we face. So what is MEDIC? MEDIC addresses this gap by identifying that, first of all, there are many performance dimensions in healthcare, that there are many end users in healthcare. You don't always have a clinician or a patient using these. Sometimes it can be nursing staff or biomedical sciences researchers or others. We also recognize that there are many different use cases. Some can be operational in nature, some could be productivity oriented, but some could be very much towards making a diagnosis, prognosis, or a treatment decision. And we look at a range of different metrics to do this. Now, what MEDIC is not, it's not a substitute for real-world testing, but we identify that, and again, when the limitations of the benchmarks like USMLE were brought forward, a lot of researchers in the community have said, hey, we know that these benchmarks are limited, but the best way to test the models is out in the real world. And we're not arguing against that. In fact, we say that MEDIC complements real-world testing. But we've got to realize that the pace of LLM development is so fast that if I take 6 months to run a study with, say, Llama 2, in that time, Meta has already come out with Llama 3, which makes my previous findings not very relevant for the capabilities of the LLMs that are available today. So therefore, it's really important that we recognize that the real-world testing represents what's called a lagging indicator of performance. And to complement this lagging indicator, we need something called a leading indicator, right, which can give us some direction upfront about where to place our bets in terms of trying out an LLM for a real-world application. And that's where this benchmark really comes in. So MEDIC has 5 important dimensions. The first one is medical reasoning. This refers to a large language model's ability to apply the prior knowledge that it has seen during training, and then use that with facts at hand to make clinical decisions about diagnosis, prognosis, drug recommendation, and so on. And a number of recent studies in JAMA and other high-impact journals have looked at assessing how well large language models do in this area. While the performance and medical reasoning is important, we also need to recognize that we need to attest for ethics and bias understanding of these models. Specifically, I note this concerning finding from a recent article in Lancet Digital Health, where they found that large language models do tend to perpetuate racial and gender biases that may have come from their training. So for these reasons, again, we ought to be closely looking at the performances of these models on things like how well they handle sensitive medical information, respect patient privacy, and so on. Now, closely related to ethics and bias is, again, something called the ability to understand medical data and the language itself. This recent article in the New England Journal of Medicine's AI journal noted that all tested large language models performed fairly poorly on medical code querying. Now, why is that interesting? Because as it turns out, electronic health records, an important form of medical information, medical data that's widely available today, are actually rich with clinical codes. And so LLMs for clinical applications not only need to be good at understanding the language and being able to reason, they also need to be able to understand these clinical codes. So we designed some of the tasks to assess both the ability to understand unstructured as well as structured data sets that we see in healthcare. Now, another important dimension of performance that's very relevant today is how well these models can adapt to novel tasks that they've not seen in the training. And this relates to something called in-context learning, where instead of training the model in advance, what you do is give it all the information it would need, essentially like an equivalent of an open book test, and then ask a question that it can answer based on the information that you've handed it over. There was a paper again in NEJM AI describing basic concepts behind how this works. It's a very popular approach called RAG. Not going to go into the details of RAG itself, but the idea again is how do we test for a model's ability to adapt to new tasks? Last but not least, we recognize that all of the performance is important, but perhaps the most important one is the patient safety itself and the risk that these technologies bring in real-world applications. And in that regard, I note the findings from this recent British Medical Journal paper, which cites that many of these models could actually be used to generate harmful medical information, misleading medical information, that can then be used for propaganda or misleading articles. So we really ought to be testing these models for a range of these different dimensions. Now, the way in which we apply these performance dimensions is through a set of different tasks, and we note how these tasks interact with the 5 dimensions of MEDIC. The check marks basically indicate the strength of the relationship that we see between each of the task type, as well as the dimensions that they help us assess. And we note that many of these different tasks actually help us test for a particular strength of the model in different ways. So before I dive into the results and give you some of the takeaway messages, a key component that we developed and introduced in this work was this notion of cross-examination, whereby to assess how well a large language model is doing, how much hallucination it suffers from, and so on, we have a 3-step process. We generate questions, a set of question and answers from the context that was provided to the large language model, as well as the answers that the LLM generated based on the provided context. And then essentially by running this cross-examination, we're able to quantify the model's performance in 4 different metrics called consistency, coverage, conformity, and conciseness. And these help us, again, tease out the strengths of the model in different ways. Now, how did the models do when we evaluated them on a range of these different dimensions? So first up, we saw that when we run the close-rendered evaluations, right, and these are the typical evaluations you'll find in most academic papers today, we see that there are a number of interesting things going on here. Among them, we notice that the clinically fine-tuned models actually tend to perform better compared to their base model, right? So for instance, if you take a look at MED42 Llama 3 8.1b, which is fourth row from the top, that performs consistently better in most cases compared to the base model, which is the Llama 3. We also notice that performance does not always depend on the size of the model itself, right? And that there is a sort of a diminishing return that applies, which is unfortunately not seen here. Looks like my PowerPoint also needs some coffee. This was supposed to be a scalable vector graphic, but basically what we have in this plot is a demonstration of how, as you go on increasing the model sizes, the performance actually flattens out. And that's important because, as we heard in some of the previous talks by Professor Hanan and others, is that this approach of throwing more brute force compute and more data doesn't always give you the sort of return that you would expect. And yeah, we have some more findings related to this particular evaluation in the paper. For instance, through the toxygen evaluation that we ran, we observed that it's not necessarily the case that larger models are safer for clinical applications. In fact, you really have to be quite intentful about designing the models to be safe, as we'll show ahead through some of the other benchmarks. I'm not quite sure why the diagrams are not appearing, but what we observed in another set of open-ended tasks is that when we looked at the model's performance on 9 different dimensions, some of which test the model's ability to understand the language and its ability to draft professional responses, we saw that, obviously the graph here is not visible, but what we observed was that in areas like professional tone, most models perform acceptably well, but there's a significant amount of contrast in performance that we observed when you look at dimensions like risk mitigation. Now, this was done in an open-ended manner. So here the models were given a prompt and asked to respond to that prompt without being given any choices. This more closely mimics the real-world situations that we often encounter in healthcare. And so we thought that this finding was particularly interesting. While the radar plots helped us illustrate the absolute performance of the model, we also did a head-on comparison for relative strength of these models. And what we found was that the clinically fine-tuned models often tend to outperform the base models that they were fine-tuned on. We also observed that larger models are not necessarily better, again. For instance, GPT-4o, which is widely believed to be a 1.8 trillion parameter model, again, so it's a secret, but that's the number that often gets cited. We see that it ranks 4 in this head-on comparison with models like MED42 and Llama 3. We also tested the model on a set of different tasks. For example, their ability to generate clinical summaries. Why is this important? If a patient goes to a clinic, the doctor has to evaluate, to look at all of their past medical information. And obviously, in a real environment, doctors don't often have the time to evaluate that at point of care. So they often rely on a manually generated summary to understand, to quickly get a sense for what the patient's past medical history has been. Now, AI has been cited widely cited as a tool that could help solve some of these challenges. When we apply this particular test of looking at clinical trial documentation from clinicaltrials.gov or problem histories and then being able to generate a summary on it, what we observe is something quite interesting. So dimensions like conformity and consistency, a lot of the models score really high on them. And these are the dimensions, as I'll show you ahead, correlate very closely with metrics like Rouge or BERT score, which are traditionally used in evaluation of the LLMs. But the story changes when you start looking at the extent of coverage as well as conciseness of the responses. You see a much greater contrast here. And This pattern in general, again, of having different trade-offs to select from, continues when we look at another set of related tasks, which was on generating a structured report based on doctor-patient interaction. Here we again similarly notice that coverage and conciseness present a very clear trade-off that you have to select from. Interestingly, there are takeaway messages here as well. We note that, for instance, in the problem of ACI bench structured reporting, OpenBio, which almost had a consistency score of 100, achieved a lower coverage score compared to models like, say, GPT-4o or MED42. So depending on your application, you really have to know what's the target profile performance that you want to achieve, and then based on that, make a selection of from the available models that you have. And this message becomes even more clear when we start plotting these model performances on the left, we have a conciseness versus coverage score, and you see this sort of a drop, which shows the trade-off here, right? Interestingly here, you see a clustering of some of the models near the ground truth. So for instance, GPT-4o and MED42, they have a characteristic that could be said to be very similar to that of a ground truth physician, right? Which I think is an interesting finding here. On the right, we see a trade-off between conformity and consistency score, and again, you see a significantly strong clustering on the right side of that plot, which tells you that there's not a lot of contrasting signal there to base your decision on for the model selection particularly. Now, looking at the safety and ethical evaluations that we did, again, some really interesting messages here. Two main ones were that the larger models are not necessarily safer, right? And second is that preference-aligned models actually tend to be safer compared to the non-preference aligned models. And the third related finding was that clinically fine-tuned models appear to be performing better than the base models that they were based on in terms of their safety profile. And here the safety profile was again judged based on looking at how easy was it to probe a model to generate clinically harmful information, misinformation, and so on, and be able to again respond with in a manner that would indicate bias against a particular demographic factor. So what are the implications here? As we discussed earlier, when we look at the 4 metrics that we derive out of our cross-examination framework, scores like coverage have a very high correlation with the traditional metrics like BERT score, Blue, and Rouge. And it's interesting that metrics like consistency, conformity, and conciseness give you a different contrast. And this sort of validates the approach, because while traditional approaches help us characterize models' performance in known ways, consistency, conformity help us tease out different profile of these model performances that are not traditionally captured, but which we found to be important for many of the clinical tasks. So, as a limitation of the model, we employed something called large language model as a judge, which uses essentially an LLM to decide among which of the 2 presented options is a better response. We had again some validation done for it against a real clinical expert to see how closely an LLM as a judge does compared to a real clinician, and the findings were that they were fairly close. The margin of error was fairly small. And yeah, I think in the interest of time, that's the last piece of, let's say, conclusion that I want to leave you with, is that there's no substitute for real-world testing, but we do need to know, again, where to place our bets on, because there are thousands of experiments you could run, and there isn't enough research funding or compute to be able to do all of those. So hopefully you'll find some of the findings here interesting for picking your LLM. Thank you.